What's up, guys? Mr. Patterson here, taking a look at section 13F, relationships between lines. Um, the general concept of this video is not going to be anything that surprises you. Specifically, we have three different types of classifications. We could have intersecting lines, of which there could be perpendicular, but we'll talk about that, at another point. We could have parallel lines, which have no solutions, and we have coincident lines, which means that they have the same exact equation there. All right, now we're going to first talk about them in two dimensions, and we're going to talk about them using row reduction, so using our linear algebra that we talked about a few chapters ago. So let's take a look at this first example. It says reduce the system using row reduction, hence describe the relationship between the pair of lines. So we have to use the row reduction before we can figure out the type of system that we have here. So we augment the matrix, right? We put it into 3, 5, 9, 2, -3, -13, and we have to make sure in this case they were both in standard form, but if they were not in standard form, we'd have to convert them to that first before we can go ahead and do this augmented matrix here. So what are we going to do? If you remember what we want to do, we want to get the first number to be 1 in the first row. Then we want row 1, sorry, we want row 2, column 1 to be a 0, and row 2, column 2 to be 1. So we're just going to transform our matrices. How do we get this first number to be a 1 when it's a 3? We're going to multiply this first row by 1/3. So 1/3 R1 becomes 1 5/3 3. This 5/3 isn't ideal, but it's not that bad either. The bottom row, we want this first number that is a 2 to become a 0. Now, if I do 2 times row 1, that gives me 2 times 3 is 6, minus 3 times R2, that's a -6. I end up getting a 0. And then I just do the same thing to account for the other values as well. All right. And then lastly, I want this last number here in row 2, column 2 to be a 1. How do I get 19 to be a 1? I multiply everything in the second row by 1/19, which luckily for us, obviously that's going to still be 0, but this number over here is 3. All right. So as soon as we look at that, we know since this is 0x plus y equals 3, that y has to be 3. And then when I substitute y equals 3 into the first equation, I end up getting x equals -2. So for that reason, I know that these two lines intersect at -2, 3. Therefore, these are intersecting lines. All right, let's take a look at this next example. It says we have x plus 3y equals 5, 4x plus 12y equals k, and it says k is just a constant, and give a geometric interpretation of the solution. So generally, this is going to be a situation where if k equals something, then the system will be something, and if k equals something else, it'll be something else. So we're going to treat this the same way. We're going to try to get it to be 1 in row 1, column 1, 0 in row 2, column 1, and a 1 in row 2, column 2. Luckily for us, the 1 is already there in row 1, column 1, so we don't have to worry about the first row at all. In row 2, however, I have 4, 12, k. How am I going to get this 4 to become a 0? Well, if I did R2 minus 4 times R1, that's 4 minus 4. That gives me 0. But when I end up doing that, I end up getting 0 in this second location here as well, row 2, column 2. So the goal was to get a 1 there. It didn't happen. What that tells me is that this is a special situation. What I end up having is 0x plus 0y equals k minus 20. All right. Well, we have a couple scenarios here. If k doesn't equal 20, right, so if k is 5 or if k is 1, whatever, then what that means is that we have an inconsistent system here because this is going to have no solutions. And if that's the case, then I'm going to have parallel lines because they have no solutions. But if k does equal 20, we end up with 0 equals 0. 0 equals 0 obviously is a true statement, and therefore we would have coincident lines. And therefore we could write our solutions using our parametric equations here. We could say, okay, we have x plus 3y equals 5. So we could just say y equals t, And then if I go to solve for x there, x equals 5 minus 3t. Now I could have said x equals t, and I would have had a slightly different value, or sorry, slightly different equation for y, but that would have been the same thing. So when we go to write our solutions, we say there are infinitely many solutions in the form of x equals 5 minus 3t, y equals t, where t is a real number. So again, we had to deal with both scenarios here. It's possible that it has no solutions because they're parallel lines, or if k does equal 20, then we have these solutions here. All right, that's it for this first part of section 13F. I'd like you guys to work on numbers 1 through 9 odd. And when you're doing number 1, just the left column. And I'll clarify that when we look at when I type it up in the Google Classroom. Have a good day. Talk to you guys soon.